Good morning, friends. I am Dr. Dwivedhi, Professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. I feel immense pleasure to give this lecture on aircraft stability and control. Today, it's my lecture number 43 and tutorial number 3. This is related with numerical related to neutral point of airplane. In the previous two tutorials, tutorial number 1 and tutorial number 2, I have discussed about how the longitudinal static stability is maintained, how many types of longitudinal static stability, how will you design the aircraft for having a longitudinal static stability, what are the conditions to be met to find and to make sure that your aircraft is longitudinal static stability, that we have covered in our unit number 1, this tutorial number 1 and tutorial number 2. Now I am here for the tutorial number 3, and in this we are going to solve very nice example of a numerical or problems. In this problem, a student will be able to design the aircraft for a given condition. If you understand this problem, it will be sure that the student from aeronautical engineering, they will be also gaining the knowledge that how you can design the aircraft and how you can vary the wing, tail and other configuration for the particular conditions. Here the problem, and it is very interesting problem. I think this will be very useful for you people to design your aircraft elevators, and for different CL conditions and for different speed, how much elevator is required, what are the location of the center of gravity and other things you can understand very well. So I am going with this problem, and all the viewers, please note that this is the one of the very best example for the designing of your elevator of the aircraft. So in a flight test of a general aviation airplane, the following data were obtained while trimming the airplane at different speeds. So here we have the different speeds. Speeds are two speeds, this is 100 meter per second and 140 meter per second. Angle of attack given in degrees. For 100 meter per second, it is 5 degree. In this 5 degree, we have the coefficient of lift 0.52. Elevator deflection in this case is 4.0 up. I told you that if it is up means it is a minus. If it is down, it is a plus. The CG location for these two cases, 35% of mean aerodynamic chord, and for 140 meter per second, angle of attack is 3 degree, coefficient of lift 0.38, elevator deflection delta E is 2 degree down, center of gravity location 35 degree, 35% of the mean aerodynamic chord. The next case is 100 meter per second, angle of attack in this case is 4 degree, coefficient of lift 0.46, elevator deflection delta E in degrees, it is 1.0 up, it means minus 1. This is at 42% of mean aerodynamic chord, the CG location. The next case is 140 meter per second is the speed of the aircraft. Angle of attack is 1 degree, coefficient of lift 0.24. Elevator deflection in this case is 1.50, down means plus 1.5, and this is at 42% of mean aerodynamic chord, the location of the center of gravity. If the lift curve slope of the aircraft is given 0.1 per degree, lift curve slope CL alpha is 0.1 per degree and variations are linear, then what we have to find out? First problem, we have to find out what is the value of stick fixed neutral point. So this stick fixed and stick free. Stick fixed normally we use as far as the designer or engineer part of this thing. When we talk about stick free, it is a pilot part, and because pilot has to apply the stick, then it is a free. But here we are fixing and it will remain there. We are not considering any aerodynamic effect after fixing. But if it is free means how much aerodynamic effect or further variation is given on the position of the stick or position of the control surfaces. So that is the difference. So here we are not considering the stick free. We are just here, all the equations are solved by using the stick fixed condition only. So here we know that the elevator required for the trim, that is delta E, is given by the following equations. These equations we have discussed in our unit 1 or module 1 very many times, and we have derived also this equation. So this delta E required is equal to minus Cm naught by Cm delta E. This Cm delta E is a dCm by delta E. This is also called the control power. Cm naught is equal to coefficient of moment at 0 degree angle of attack. XCG minus XNP is equal to here static margin, and this is the same, and this is the CL trim. Now putting this value from the given table. In the given table, delta E is equal to minus 4 means upward, and 2 is for the downward. So here you can see that the first equation, if you put this value in this equation, minus 4 is equal to Cm naught minus Cm naught by Cm delta E minus XCG is given 35%. So 0.35 minus XNP divided by Cm delta E into 0.52. This CL is given in the table. Same for the another case, for 2 degree downwards, it is a plus minus Cm naught by Cm delta E minus 0.35 minus XNP Cm delta E into 0.38. This is the equation number 2. Now we have to go for the next case. Now if we subtract from equation 1 to 2, we will get minus 6 is equal to minus 35 minus XNP by Cm delta E, 0.38 minus 0.52 Cm delta E. Now we have to make a simplify. So here we will get minus 42.857 Cm delta E is equal to 0.35 minus XNP. This is the equation number 3. So this is for the first two cases. Now similarly for the 42% of the CG, this is for 35% of the CG. So now the location of the center of gravity of the aircraft is 42%. So here it is given minus 1 delta E minus Cm naught by Cm delta E minus 0.42 minus X bar NP divided by Cm delta E 0.46. These all things are given. Here also it is a downwards 1.5 degree minus Cm naught Cm delta E 0.42 minus XNP Cm delta E. This is the 4 and 5th. Now we have to subtract from 5 to 4 to 5. Then we will get here minus 2.5 is equal to 0.42 minus XNP divided by Cm delta E. 0.24 minus 0.46. You will get here minus 11.363 Cm delta E is equal to 0.42 X bar NP. So this is the sixth equation. Now two equations we got and two unknown. These two unknowns are Cm delta E and XNP. But we are interested to find out only XNP. So here if we solve these two equations, we will get X bar NP is equal to 0.445. So it means this is a 44.5 of the chord. The location of the neutral point of the aircraft is 44%, 44.5. So if you see, what is the meaning? If this is the nose and this is the tail, NP, from here this will go, this is the NP is 44.5%. So NP is located here. That is the meaning of, and your CG is before that. One is 35%, another is 42%. Means before, if this is the before, then it is stable. That we can understand by seeing the location of the CG and the location of NP. If the CG is before the NP, it is stable. So here 35 and 42, we can say that aircraft is longitudinal statically stable. Now the problem number 2 we have to solve. I think it is, you have understood very well that how to find out the stick fixed neutral point. Now it is very simple. We know that find the most aft location of the center of gravity such that the aircraft has a minimum stability margin of 5%. Means stability margin SM is equal to 5%. We know that SM is given by X bar NP minus X bar CG. SM is given 5% of the C bar is equal to 1. So 5 by 100 it is equal to 0.05. SM is 0.05 is equal to XNP. Just we have find out 0.445 minus XCG. So what will be the CG location? The CG location will be 0.445 minus 0.05. So CG location will be 0.395. So if I draw the line here, this is the front part and this is the tail part. So you got here neutral point, we got here, this is the 50, this is the neutral point 44.5, and your CG location is here 39.5. So your CG is here and this is the NP is here. So it is behind and this is called static margin. So your aircraft is longitudinal stable. You can say by seeing this parameters, you can say that your aircraft is longitudinal stable. So now next case. In this only, if we increase this to 12%, here it is not 10, it is a 12%. Okay, sorry, I have made the wrong here. Now we have to find out most aft location of the center of gravity such that the aircraft has a minimum stability margin of 12%. In the previous case, it was the 5%. Now in this new case, we have the 12% of. So as in the previous, the static margin is now 12% of the chord. We know that the static margin SM is given by SM is equal to X bar NP minus X bar CG. SM static margin is given 12%. So 12 by 100, this is 0.12. So this 0.12 is equal to XNP is 0.445 minus XCG. So XCG is equal to 0.445 minus 0.12. So it is 0.325 or 32.5% of the chord. So if you see the previous one and this one, if you see here, just I am writing here, this is the nose here, this is the tail, this is the NP. NP is at 44.5. So this CG is 32.5. This is the CG location, 32 and this is the 44.5. So in the previous, if you see, it is 39.5. It means it is very close to the neutral point. This much close is not very good. So to have a very good longitudinal static stability, we should have a sufficient amount of static margin. The static margin is the difference between the neutral point and the center of gravity location. So in this, we can see that it is at 12%. So it is very safe and very sufficient margin is there to have the static stability. Now, whatever we have got the result in this problem, I have given in a nutshell. I have made one aircraft, and this first we have find out that neutral point X and P. We have find out that we have got 0.445. This is also 44.5% of C. Most off location of the CG when static margin is 5%. We got this CG1 is 0.395 or 39.5%, and CG2 we got 32.5%. Okay, this we have got. I have represented here. This is the nose. From nose, this is the neutral point. Neutral point should be the behind than the CG, and fortunately here CG1 and CG2 both are ahead of the neutral point. So it is a stable, but which one is a more stable? That we have to understand. So here we can say that the CG2, which is much ahead than the CG1. So the location of the center of gravity, if you keep on the CG2, that is the 32.5% of the chord length, then you have sufficient static margin and the motion, and you can also vary different loading of the aircraft. If the CG is very close to the neutral point, we cannot vary the goods, luggage, bombs, armament, fuel and other things. So we should have a sufficient nearly 12 to 15% of the static margin so that we can properly accommodate all types of passengers, cargo, weapons, armament for different types of roles. So here I have shown here that this is the this is as a C. So these locations are given as per that. So we can see for less static margin, that is CG1 is limited to 39.5%. However, for 12% CG range is more, that is it is 32.5. Okay, so a sufficient amount of this thing is there, and the gap, the limitations are much better for CG2 location. Means where the static margin is 12%, there we have a sufficient amount of stability. Okay, so I have completed my lecture number 13 and hope this will be very useful for you, and this might have given some input about neutral point location, center of gravity location, and how these two points relate with each other, so that we can assess that aircraft is stable in longitudinal. To have a better accommodation for goods, cargo, passengers, fuel, armament and other things, we need a sufficient amount of static margin. As you can see in this diagram, that CG2, which has 12% margin, is better equipped for different CG variations. Thank you very much for joining, and hope you will be listening my next lectures. I will come with few more very nice examples and some practical issues related to the aircraft stability and control in coming tutorials. And after this tutorials, I will be trying to complete some question answer session In that, I will take some typical questions and I will answer in my lectures. Thank you very much for joining. See you again. Please tune to my YouTube video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.